Hello everyone, my name is Jing Wen, a new PhD student from Beijing Normal University, and the topic of my presentation today is mass loss rate of highly evolved stars in the Magellanic Clouds. And this presentation is divided into 4 parts: research background, method, result and discussion, and finally the conclusion. Let's begin with the background. Explain why we are interested in this field, and there are a few key points. First, during the AGB phase, stars produce many elements found in the universe, and AGB stars lost mass at high rates, making them major contributors to the cosmic dust. And second, mass loss during the RSG phase impacts the star's outcome. And third, the precise mechanism driving mass loss is still unclear. Various methods are currently employed to estimate mass loss rate. However, there are significant discrepancies in results among the different studies, which may arise from differences in method, models, and samples. And so, using a unified method to study a larger sample to obtain the statistical result is beneficial for subsequent research. And Ren et al. 2021 construct a evolved star catalog for local groups. So the RSG and AGB candidates we used are from their catalog. This catalog includes over 40,000 evolved stars in Magellanic Clouds. And to estimate mass loss rate or dust production rate using the SED fitting method, it is necessary to construct a SED which covering a wide range of wavelengths. So we cross-match our initial sample with various data sets such as SkyMapper, MCPS, Gaia et al. And then we filtered this data, filtered data-based this selection criteria such as error, signal, noise ratio of lag et al. And so finally, we obtained, around 1,300 sources were removed. And the second part of our method is model. Using 2 dust relative transfer codes and setting parameters of circumstellar dust, we generated a new template library containing over 800,000 SEDs based on max models. And this table shows all our parameter settings, includes photosphere model and dust shell properties and the dust grain parameters. And then we filtered this model based on the dust temperature at inner radius and the metallicity. Finally, we obtained over 70,000 models for Magellanic Clouds, which were used to fit it with SED, observed SED. The second part of our method is the fitting. We classified all our evolved stars into 3 distinct chemical types based on the best fitting model with the minimal chi-square. Oxygen-rich stars, carbon-rich stars, and optically thin stars. And this figure shows several examples of SED fitting results. And different panel shows the different chemical types evolved stars and the dispersed and the scattered points with different shapes and colors represent different observations, and the black line represents the best fitting model. And we also classified AGB stars with 2 mass J minus KS greater than 2.0 and asked them extreme AGB stars. And finally, we compared our result with the spectrum. As shown in this figure, the red line represents the spectrum from IRS. And we found that the classification accuracy exceeds 80%. Okay, let's move on the result and discussion. Based on the SED fitting result, we provide a catalog of over 40,000 evolved stars in Magellanic Clouds. This table includes dust shell parameters such as chemical types, dust temperature, optical depths, and dust mass, and also includes the stellar parameters such as luminosity, which obtained by integrate observed SED or best fitting model SED, and effective temperature and mass at all. And we also provide a statistical result of dust production for evolved stars in different galaxies, as shown in these tables. And we divide the result and discussion into two parts, focusing on RSG and AGB respectively. First, let's talk about the result of red supergiant stars. We note that the mean DPR dust production rate for RSG in SMC lower than that in LMC. And the left figure shows the distribution of dust production of red supergiant stars in different galaxies, and the different colors represent different chemical types. We note that the SMC seems to have a higher proportion of optically thin stars than LMC, and the photo figure shows the stellar parameters distribution of different galaxies. From left to the right, display the optical depths, effective temperature, and the luminosity respectively. And the different color represent different chemical types. We observed that the high dust production rates, oxygen-rich stars are more common in the LMC than SMC. So combining this information and these figures, we might be able to draw a conclusion that as the metallicity decreases, the proportion of optically thin stars increases, and the number of high dust production rate oxygen-rich stars decreases, and the mean dust production of RSG stars drops, and mean effective temperature rises. It is the same for AGB stars in our result. And next is about the AGB stars. This figure shows the dust production rate distribution of AGB stars in different galaxies, and the green line represents the extreme AGB stars, which have the highest dust production rate. And we note that a few evolved stars play a key role in the dust production rate estimation, and the contribution from carbon-rich and oxygen-rich AGB stars are not significantly different. And in Small Magellanic Clouds, the contribution of carbon stars is greater than in the LMC, but it is not very obvious. And we would like to emphasize the high uncertainty in dust production or mass loss rate calculation. This table shows the effect of different parameter settings on dust production rate. And we can see that the calculation of the dust production rate is highly influenced by parameter settings and data. And our result is just an estimation based on current data and method. And then we also study the relation between dust production rate or mass loss rate and the stellar parameter. First is the luminosity, and this figure shows the luminosity versus mass loss rates, and different panel shows the different chemical types AGB stars and red supergiant stars, and the red line represents our fitting results, and the various color represents the previous work from literature. And we found the luminosity mass loss relation of AGB stars is highly dispersed, which shows the complexity of AGB stars. and a simple luminosity mass loss relation might be meaningless and not applicable to stellar evolution models. However, accuracy in the luminosity mass loss rate relation can be improved by classifying AGB stars. And for red supergiant stars, we found the obvious turning point at a log luminosity equal to 4.4 at this figure and this panel, both in LMC and SMC. And position is very important feature for AGB stars. So we also studied the relation between dust production rate and the period amplitude. This figure, the up row of this figure shows the proportion of carbon-rich AGB stars increases as the position sequence evolves from the left to the right, from the 4 to 1. And the change and the second row and the third row, in the second row and third row, the color bar represents the value of dust production rate. The second row shows the changes in dust production rate on the period magnitude diagram. And the third row shows the changes in the dust production rate on the period amplitude diagram. And we can draw a conclusion that the dust production rate of AGB stars with a position period of about 300 days and I-band amplitude greater than 0.5 show a sharply increases like this. And finally, there is a conclusion. We provide a catalog of evolved stars that includes both stellar parameters and dust shell parameters. And we reviewed that the total DPR of Magellanic Clouds, and we explored the relation between stellar parameters and the mass loss rate or dust production rate. And we found a turning point at the luminosity mass loss rate diagram of red supergiant stars. And we found the metallicity has some impact on dust production of oxygen-rich stars. With lower metallicity seems to result in lower mean dust production and higher optical lething proportion. That's all. Thank you.
It's only a comment that there is an impact for sure on the dust production rate by the metallicity, but we should also consider the star formation history that is different. There is a star formation history in the two galaxies, and this has been analyzed in the last years, and so you can also consider this in your conclusion.
Oh, so you mean I should consider more factors? Okay. Thank you.
You're welcome.
Nice work. So my question is, do you model the same way the AGB stars and the red supergiants for the mass loss rates? Because the mechanism could be considered different.
You mean AGB stars it might have some difference from red supergiant stars?
Yeah, the way the mechanism of mass loss. So when you model these stars,
it seems no obvious difference between the fitting process.
okay.
Thank you.
Can you tell me how you calculate the dust production rate and how you can distinguish between stars that have been like AGB stars longer and had more opportunity to make dust?
The dust production rate is provided from the this relative transfer codes, and it's like the dusty, but